So today I'm going to speak about this very interesting project in Delhi that we are doing, World Trade Center. And so here we are not the principal consultant, but we are designing the very special central crown structure, which happens to be a rooftop restaurant. As you can see in the 3D image here, the central curvy portion is the feature element of this project, which is done completely in structural steel supported by RCC core. So that is the part that we are designing. And I'll take you through the structural design process for this structure. So just to give you a brief detail about the project, it is developed by NBCC India, and the project architects are SA Architects, and PMC being SICA, and EPC contractors are NCC, and so Sanghvi Associates are the principal consultants who are responsible for all the RCC design, and we are on board on this project to design the structural steel parts. So here, we were originally appointed only to peer review the special feature part of the structure, but we came up with very good ideas to optimize the structure, and we proposed that we could reduce the steel consumption by 20%. So hence, we were given the job of doing the detailed design for this part. So as you can see in the center, it's a 2-story tall restaurant featuring, and it is spanning in between the two official buildings. And in the center, if you can see clearly, there is a core going on, which is unsupported from ground to 7th floor. And on the 7th floor, it is supporting the central portion of this restaurant structure. Some more detail about the project. So as I earlier mentioned, the restaurant part is divided into 2 parts. I mean, the 3 parts basically, 2 side wings and 1 central wing. And these are, for structural simplification, these are separated out by expansion joints of 350 mm wide. So I will focus on the central wing here because this is the more challenging portion. And as you can see, the elevation of these trusses, on the rear side, we have 13-meter long cantilever span, which is supported by a steel box girder, which is tapered toward the end. And on the rear side, we can see a 7.7-meter long cantilever span. And also on top of these box girders, the framing is designed so that it acts as a Virendale frame. A little bit about the structural behavior here. So on the left side, you are seeing the plan, the structural layout of this floor. Here on the periphery, top and bottom side, the yellow lines are representing 2-floor deep trusses, which are forming the elevation of this building. And on the sides, the red lines are indicating the deep girders. And because of this, we are getting a very stiff perimeter frame. And so normally what we are used to see is that in case of a cantilever structure, the deflections are more towards the tip of the cantilever. But because of a very stiff outer frame, we are seeing the deformation patterns such that the deformations are occurring near the center. In the right side, you will see the deflection contours under gravity loads. Now, these are the bending moments of this frame. So on the left side, we are seeing the bending moments on the girder floor. The red triangles are indicating the cantilever bending moment in the RCC girders. The steel plate girders. And on the right side is the typical floor plan where we can see the normal distribution of bending moments. So here I'm trying to explain the behavior of Virendale frame. On the left side top, we are seeing the ETABS model elevation with undeformed shape. And on the right side, you will see the deflected shape of the same frame. Now this deflected shape is significantly scaled up just to understand the deflection behavior. It is not the actual case. And on the left side bottom, the axial force diagram, that we would hope to see a compression coming in the bottom and tension on the top elements of the virendil. That is what we are achieving. And right side bottom, we are seeing the bending moments for the virendil frame. And here, the main thing is to notice is that the connections of these virendil frames are not pinned, they are fixed in order to get more stiffness out of them. So this is one of the main reasons we were able to reduce the deflections. And since the deflections were reduced, we were able to optimize the sections further. So this is one slide related to 5 times designing the cantilevers for 5 times the vertical seismic shaking as per the latest 1893 code. So here we have tried to simplify this process by, so there is a AV factor, and AV factor, the expression is given in the code that you can see in the top left. So this is the expression given in code, and we were able to simplify this equation in terms of dead load and live load so that we don't have to run a separate modal analysis for Z direction. I'm sorry for getting too much technical here, but this is, in short, I can say that we have simplified this approach so that we could simplify the design, as well as this also helped us in reducing the forces due to earthquake, for Z direction especially. So here we can see the 3D ETABS model, which are used for analysis. And on the right side, we can see deformation shape, which is scaled up. Yeah, so this was, I was talking about that structural optimization. So, in the beginning, we thought that we will be able to reduce the consumption by 20%. But while, in the process of detailed designs, we were required to do some other changes. But still, in the end, we were able to reduce up to 18% almost, which is a significant figure. And that totals up to 150 tons of steel. And this is a 672-ton project. Reasons why we were able to do this was that, first of all, we converted the normal RCC slabs to deck sheet slabs, composite deck sheets, and that helped us reduce the self-weight by 15%. And then we stiffened the virendil systems more so that we could allow more deflection in the frames and hence reduce the material consumption or reduce the sizes of the members. So we also tried to make this design erection friendly. So our contractors were very keen to have a modular erection, whereas the entire structure is divided into 2 portions for the central wing. And on the image you are seeing on the left side is the front module. And this is a module which will be lifted from, the process would be that these modules are erected on site, on ground, and then lifted to its original positions or the intended final position by the help of cables, cranes, and strand jacks. So even in this condition, we had to check the analysis so that while lifting the modules with the crane, there should not be any excessive deformations or yielding. Here, you will be able to understand the erection strategy of rear module, where you can see since we have a very good advantage of adjoining towers, we could fabricate some temporary trusses to lift the modules in place. Similar strategy for the rear module, which is a longer truss. Here now, if we talk about a 13-meter cantilever girder, which is supported, it is locked in to the RCC core via this connection. So in case of this structure, there are no other redundancies. So connecting the steel structure to the RCC core was a big challenge. So here we have designed this connection keeping in mind that we should get at least a factor of safety of 2.5 because there are no other redundancies. So in order to do that, we had to give this very heavy anchorage system inside the core walls to lock the cantilever girders in place. Now, in the image, you might not be able to understand the full scale of it. So in the next image, I'll show you the real fabricated insert plate. If you can see, it is double the height of a normal human. So it's 11 feet tall, just insert plate. This is the insert plate connecting the steel structure to the RCC core. And on the rear side, you can see all the anchor plates which are inserted inside the RCC core walls. And while designing this anchor plate, we also had to keep in mind that it should not interfere with the reinforcement of the RCC wall. So it is provisioned in that way as well. So I have a few more slides about highlighting the connections. So here, instead of using normal gusset plates which are visible in elevation, we were able to trim the gusset plates in such a way that it does not have any more projections outside the junctions. And so in this project, because of all the different sizes of elements, we had around more than 300 numbers of connections to design. And being a government project, there were 2 peer reviewers. And also we had to submit a complete submission package to IIT for approval. So all the 300 connections, we were required to submit designs, detailed calculations. So we used the software called as Idea Statica, which allowed us to do all this and perform all the necessary checks and also take out all the detailed reports. And the images and the stress contours you are seeing are from Idea Statica. So we have designed and modeled each and every connection in this software to check it in all the, under all the design load cases. So these are the star brace connections. And in this slide, I'm showing the column base plate connections and the stress contour. And on the left side, there is drawing. These are some beam-to-beam connections, typical ones. On the top right side, we are seeing the stresses in the plates. And on the bottom left side, we are seeing the buckling patterns. So thank you so much. That was my time. And this is the actual picture of the site. The site is currently in progress. And on the right side bottom, you'll see the completed artist's impression image.